I did record last time, but I didn't record the whole thing. So I put up the stuff from what I'd written down on my iPad. I posted that too, so you guys would have that. But today I've got the recording on.
Okay.
So that's you guys. And the
All
thing
right,
is,
'cause
I need to go back in and just set it to automatically record. But I don't like to add all the stuff from the beginning, you know, where we're maybe just talking about our weekends or whatever. So anyway,
Right.
This one's recording. We should be good. Other questions? Let's see. Catch up on chat. Looks like everybody checked in.
Hey, Phoebe, I'm going to be leaving a bit early today. I just want to let you know before you just see me disappear.
Okay, thanks, Aaron.
Yep, no problem.
And we won't be here the whole time if you guys don't ask questions. So ask away.
What are we supposed to be through by today?
So where should we be through by today? Well, all of those homework assignments, let me see, a different looking schedule for everything. All of those homework assignments, I think I have due on the 23rd. Does that sound right?
Wednesday, right?
That's Wednesday at midnight. I just checked.
On the 23rd, Wednesday night?
Yep.
Yeah. And then, what I did is I just kind of jumped these in sections. So the homework assignments are just all due a few days before the test. So, but I would say really where you should be more theoretically is if you're working on the work and force problems and the work and pumping water problems, you're in pretty good shape. I would say you should definitely be done with everything through area of a surface of revolution. That would be kind of, and that one's on the border. So that's, then we worked on mass and density, work and force last time, and the pumping water problem. So you should be at least kind of maybe starting those and finishing them. The 23rd is Wednesday, so you have a couple of days. We are gonna look a little bit at hyperbolic functions. This is gonna be differentiating and integrating. So we're gonna be back to sort of more like standard calculus problems, crunching things out, and these aren't really too difficult. There are several additional formulas, but I'm not going to have you memorize all of them. It's kind of not worth our time. There are so many. So if you know the basic formulas, you should be good. And I have a worksheet in here to share with you today too.
Do you have them all memorized?
Do I? Pretty much. Yeah, I think so. I mean, there are some formulas I don't have memorized, but all of the ones we're going to do today, maybe not all the identities, but I'll give you a trick. You don't really have to memorize all the identities ever. If you can remember one, you can usually get the rest of them for free or for a little bit of algebra manipulation. Was that you, Gabe, asking me if I had them all memorized?
Yeah.
I thought so. Just checking.
Okay.
Let's see. I want to actually send you guys a document. Okay, so I just put a PDF in the chat that deals with hyperbolic functions. So let me know, did you guys get that? And you can open it, hopefully. At least somewhere. And even you should even be able to open on a phone if you need to.
Yeah, we got it.
All right, cool. All right, so you guys are quiet today, so no questions? Just kind of working along?
Yep, pretty much.
Okay.
Yep.
All right, what's this thing yelling at me about? All right. Shoot, that didn't work. Really? You're gonna make me do this? Okay, so hyperbolic functions, can you guys see that? I am not seeing, it's not really catching up. What are you guys seeing on the screen right now?
Nothing.
Yeah, it's something weird going. I'm getting a fuzzy, odd screen that's like one of the places. Yeah, that's what it looks like to me too, Nick, on my, oh, there we go. Maybe we're catching up. Or maybe it just quit sharing. Looks like the screen share ended. Let's try that again. Hmm. All right, so I can share at that screen, but as soon as I leave Zoom, let me try this. There we go. Okay. Now we got it. So I want to show you a couple of things about this. The first one, I'm just going to look at the definitions, and then we're going to kind of go back and see where some of this came from. So you guys know the 6 trig functions, right? Sine, cosine, tangent, cotangent, secant, and cosecant.
Yeah.
And those are all defined in terms of the unit circle. Do you remember the unit circle definitions for the trig functions?
Yeah.
Okay. So for example, on the unit circle, the x coordinate is the cosine, the y coordinate is the sine, and my screen share just ended. This is so weird. Okay, so we've got that info. And luckily you guys have this worksheet because I sent it to you. So you can also view it there if you open it from the chat. What we're going to do here is we're going to define what we call the hyperbolic trig functions, or just the hyperbolic functions. And these are defined, instead of using the unit circle, using a unit hyperbola. So we could go through and develop all of the definitions from it. We're not going to spend too much time on that, but I am going to draw a couple of pictures for you just to show you the difference between the definitions and how these are related. So you'll notice also that these are defined using exponential functions. So hyperbolic sine and cosine are really just combinations of e to the x and e to the minus x. Notice for the cosine, we're averaging those numbers, e to the x plus e to the minus x over 2. And for sine, we are taking the difference of those and dividing by 2. And you can only see that not from my screen, but from the document itself if you opened it up. Let me see if I can share screen from my computer. I'm not sure why this is.
Should we be taking notes on should we write all those hyperbolic functions down?
Well, I mean, I would, right? So but you could also just use the printed out copy of that. I think it is a good idea to always write things down, because every time it passes through your pencil, it has to pass through your brain at least in some way. I'm going to try one more time. Okay, so it looks like I'm just having some sort of network connection problem.
Hey Phoebe, maybe try opening it in a different browser, like Firefox or.
Yeah, it's not that. There's some sort of connection problem. I'm on the I'm in the app on my iPad is where I'm having trouble.
Okay.
So I'm just gonna it actually kicked me out of the meeting. So I'm gonna just see if I can get back in. Okay, I think I'm back, but for how long, I don't know. All right, so here are these functions. We're gonna look at graphs in just a minute. And notice something about the connections between these. So the hyperbolic tangent is actually defined as the hyperbolic sine over the hyperbolic cosine. So that is just as we would expect it. No real surprises there. It just means that this definition is a little bit funky in terms of graphs. Same for cotangent, same for secant. And the way we pronounce these is kind of weird. So for example, S-I-N-H, we pronounce cinch. And C-O-S-H, you can pronounce kosh or kosh. And I've been kicked off again. Ugh.
We can still hear you.
Yeah, I know. Because you can hear me from my computer. It's just that it keeps booting me from my iPad for some reason.
Oh,
It makes no sense whatsoever. I could be having network issues here, but I usually don't. I mean,
maybe you can pull the document up on your phone. Or is it, are you using your iPad to look at the document? Is that what you're saying?
oh yeah, and I can see the document fine on my iPad. It's just dumping me out of Zoom on my iPad, so you guys can't see it. So we won't worry about it. I'll assume that you guys can open it up and see it. I could. Has everybody got it open? Let me ask that.
Yeah, I do.
Because if you guys all can get to it and open it, then I don't have to worry about the fact that I can't screen share it. Okay, and if we slide down, we'll come back to the identities, but let's take a look at the graphs of the functions. So the 6 graphs are at the bottom of that first page. The hyperbolic sine, sinh, almost looks like I don't know, it almost looks like a tangent curve. But something to note of that is that that graph doesn't have vertical asymptotes. So it looks kind of like it has vertical asymptotes, but it doesn't. Notice that in the definition, the hyperbolic sine is defined for all x values. So there aren't going to be any vertical asymptotes. The graph is just getting steep to the right and steep to the left. Hyperbolic cosine is similar, although it looks more like a parabola. It's not a parabola. It's the type of curve there. Does anybody know what the hyperbolic cosine is? The shape. Here's a hint. It's like hanging cables. So if you were just letting a cable hang loosely from a support, you get this shape. Has anybody heard of this before?
Can you use the whiteboard in Zoom to draw it after someone answers?
Yeah.
Okay, cool.
Yeah, Merrick, I put it in the chat. So can you get to it there? And actually, let's just do this. I hate this version of Zoom. Okay, there we go. All right, so now you should be able to see that again, that hyperbolic functions worksheet, and it's back. I'm just sharing from my computer now, so I shouldn't get knocked off. And there are those graphs. So this hyperbolic cosine that kind of looks like a parabola, and it's really a sum of exponential functions, is what we would consider a hanging cable. So think about a cable just sort of hanging loosely from a couple of supports, evenly spaced, and then you just get this sort of loose look. It's a little bit looser than, say, a parabola. So the
Talking about cosine, right?
The cosine, the hyperbolic cosine.
Sorry to interrupt.
And the shape of this curve is called a catenary. Has anybody heard of catenary?
Catenary, right?
Catenary, yep. And there is a famous catenary in the United States. It's actually upside down though. So picture that catenary upside down and think of a famous landmark that might be shaped like that. Any ideas?
If it was flipped upside down.
It was flipped upside down.
A bridge?
It's not a
It
bridge.
was a bridge of sorts.
There could be bridges where you would use that, but this one, the famous one I'm thinking of, is not a bridge.
The beam in Chicago?
Oh, interesting. No, not the beam. I love the beam though.
The arches on top of the bridge.
Oh, you're getting close. The arches on top of the bridge. Think arches. I'm thinking of a specific arch that I believe is 630 feet high.
I don't know.
Somewhere near the middle of the country. All right, we'll leave it at that. I'm not going to tell you quite yet. Okay, so then you have some other functions. The
In
tangent.
Missouri?
What was that?
Is it in Missouri?
It is in Missouri.
Is it St. Louis? Something
Yeah,
to St.
yeah, the Gateway Arch in St. Louis. We see the tanh function, which is the cinch divided by the cosh. So you see these odd things. And again, now in this case, it looks like there's a horizontal asymptote, and we could see whether there is by thinking about this function. As x approaches positive infinity, notice these e to the minus x's would head off towards 0. So there might be some limit there that we approach. It looks like a horizontal asymptote at 1 and a horizontal asymptote at -1. Those are in reality there. Cosech, so the reciprocal of cinch. Notice it does have a vertical asymptote. Sech of x, the reciprocal of cosh, is defined everywhere because the cosh function is never 0. And this almost looks like a normal bell curve, similar in many ways. And then coth, sort of like goth, the reciprocal of tanh, and this one has some horizontal and vertical asymptotes. So it's kind of the strangest. We're going to focus our work probably mainly on the top 3, although the others will come into play as well. Applications will mostly have to do with those catenaries. So
Now the catenary is for the cotangent, right? Or not cotangent, sorry. Time?
cosine, yep. Cosh or cosh.
Or cosh, yeah, okay.
Yeah, and it's just a made-up way to say it. So
Doesn't it look like a parabola? Or
it does look like a parabola. It's not
It's not.
exactly the same though, because a parabola is actually defined geometrically as specifically the set of all points that are equidistant from a fixed point and a fixed line.
And they're not.
And that fixed point is the focus of the parabola, and the fixed line
Vertex.
is the directrix. You guys remember that?
Oh yeah.
The old geometry stuff that you probably haven't looked at in a long time. So we're not going to dwell on definitions of parabolas, but this is not quite the same thing.
It'd be -1 in the example on the graph, right? The directrix.
Well, if this were a parabola,
Yeah.
not necessarily.
Oh.
Not necessarily. It depends on how wide that's opening. So
Oh.
yeah, if it were a parabola, we could talk about the directrix, but since it's not, we won't.
Okay. But I mean, if you were just take a guess, I mean,
It would be, yeah, it would definitely be something below that sort of vertex point, that minimum point.
right. Okay. Cool.
And then the focus would be somewhere up in here. Okay, I'm gonna kill that. Now I'm gonna back up a little bit, and then I'm gonna try to go to the whiteboard, but I don't think I'm gonna try to go with my iPad because it's behaving too badly. So I'll just try to go to whiteboard here. Notice the identities. So there are what, 1, 2, 3, 4, 5, 6, 7, 8, 9 identities here. You do not need to memorize these, but you should sort of have them at the ready in case you want to use them. The one that I want to point out first, this very first one, cosh squared x minus sinh squared x equals 1, that should look a little bit like the Pythagorean identity that you have for regular cosine and sine. There's one big difference. What is it? If this was cosine squared x and sine squared x, what sign would you have between those? Isn't it cosine squared x plus sine squared x equals 1?
It should be plus.
Yes. So on these identities, there are little sign issues on these three Pythagorean type identities. So the signs change. This is a minus. This is a minus. Yeah, that's a minus, where they would have all been pluses in the regular trig function identity. This says that the cosh is an even function. In other words, if you substitute negative x for x, you get the same y value. It's symmetric about the y-axis, and we can see that on the graph. This one says sinh is an odd function. In other words, if you separate x or substitute negative x for x, you get the opposite of the original function. It's symmetric about the origin. Tanh, also symmetric about the origin. Cosech, symmetric about the origin. Cotanh, about the origin. And then sech, like cosh, symmetric about the y-axis. So only the two in the middle are symmetric about the y-axis. The others are all symmetric about the origin. All right. And then next we have some formulas for derivatives, but we're going to get to those in a minute. So,
Quick question.
Shoot.
Some under it's like the second, it's like right above the graphs. There's the cosh or cosh. How do you say it? Cosh?
Yeah, I say cosh.
Okay. Cosh of 2x. Oh, cosh of 2x. There's like three different, are those all three different variations?
They're all three valid. And if you remember right, we had three double angle formulas for cosine of 2x as well.
Right.
Yep.
I just wanted to make sure I was reading that right.
So you're right. And so those are three different identities that you could use if you needed to rewrite cosh of 2x in some scenario. And so you definitely don't need to memorize these, but remember that they're here as a handy sort of.
Is that a x minus 1? Or I mean, sorry, is that a 2 cosh squared?
The bottom one?
1? Yeah.
Yeah, it had a typo in it and I just fixed it because I can't find the original document. So yes, that's a -1. Okay, so let's go. I'm going to go ahead and stop the share. We're going to see how good I can do this. And so now I'm going to screen share again. No, why is that not working? Advanced sharing options. Why can't I get to the whiteboard?
Is that parent function for the cosh? Does that always start at 1 0? Or I mean 0 1?
0 1. That would be that's the basic function. Yes.
Okay, cool.
I mean, because that's that function. So for example, in thinking about parent functions, if you had cosh x plus 1, you would just raise the whole thing up 1 unit.
That would be at 2.
So that's what you were thinking about. Yeah.
Okay, cool. Yeah, I just want to make sure.
Okay. War is not giving me my. And yeah, I think I answered that, Nick. The Gateway Arch is in St. Louis, just looking back at the chat. Here we go. Okay, so I hope you guys see the whiteboard now. All right, this is going to be a little ugly because this is me having to draw with my trackpad. So we've got a really ugly looking graph, and I'm going to do two things here. I'm going to draw the unit circle, hopefully reasonably circular. Yeah, could be worse. And then I'm going to draw the unit hyperbola, which looks like this, kind of. Okay. Probably have done that on Desmos too. So can you guys see a unit circle and a unit hyperbola? I'm going to put equations in here. Okay, so the unit circle, remember, was x squared plus y squared equals 1. And we defined the cosine of an angle as the x value. I'm not going to put all 6 trig functions here because the rest of them, not a t. Undo. And the sine of an angle as the y value. So where these hyperbolic functions came from is that we do the same thing, but instead of starting with the unit circle, so there's theta is in there. Theta is really bad. Okay. Instead of starting with the unit circle, we start with the unit hyperbola. So the graph with equation x squared minus y squared equals 1. And we defined the cosine of the angle as the x value, or the hyperbolic cosine, my h in there, as the x value, and the hyperbolic sine of an angle. My I is really almost missing because I can't write like this, as the y value. We pick an x, y on the curve. And then we can show that these definitions are consistent with, and we're not going to do this in class because this would take us a class day or so, are consistent with those definitions that you have on the worksheet. For example, the fact that the hyperbolic cosine of a real number is just e to the x plus e to the minus x over 2. So I have a thought and a feeling about what's going on here. And I'm wondering.
Hey Phoebe, is that a theta right there? Cos of theta and sine of theta on the left?
Right here.
Oh, I guess
both of them are. These are thetas. And this is supposed to be a theta. This is supposed to be where theta is, up in this circle. And then theta.
The right angle in the on the top left one, or no?
Top left one?
Yeah.
Yes, those are thetas. Cosine theta, sine theta.
All right, cool. And then that's just a point, right? X comma y.
X comma y is just any point.
Cool.
I just happened to draw it in quadrant 1. So we're not going to really dwell too much on going back to this definition. We're going to focus more on these definitions that relate to that picture that looks like the hanging cable, for example, for hyperbolic cosine. And if we think about those, I just want us to take this one, and remember this is an X. It doesn't look like an X there. I fixed it. That's better. If I take this and try to find the derivative, so we're going to do one of these from scratch. If I try to find the derivative, the 2 in the bottom is a constant, so it's going to stay there. And I'm going to just differentiate the numerator. What is the derivative of e to the x?
E to the X.
E to the x, because e stands for easy. And what is the derivative of e to the minus x?
Negative E to the X. Or negative E to the X,
Yeah.
I mean.
Yes, negative e to the minus x. So notice though that this is the hyperbolic sign. Now let's go the other way. What if I take the derivative of hyperbolic sign? Well, again, the 2 in the denominator is a constant. The derivative of e to the x is e to the x. And the derivative of e to the minus x is minus e to the minus x, but we've already got a minus sign here. So I end up with a plus, and I get the hyperbolic cosine. So unlike our regular trig functions, hyperbolic sine and hyperbolic cosine are both derivatives of each other, which is kind of nice because it means that we don't have that opportunity to make a sign error, S-I-G-N error, with derivatives of hyperbolic cosine and hyperbolic sine. They both get positive signs in them. So now I'm going to go back and I'm going to stop this share. And I'm going to go back and share this thing again. And we're going to scroll down to the top of the second page. And here are the 6 sort of basic derivative and integral formulas for hyperbolic functions. Notice that in this case, the derivatives of hyperbolic sine, cosine, and tangent all get positive signs in their derivatives. Other than that, they look exactly like the derivatives of the regular trig functions. So in some ways, they're not really difficult to memorize because the only difference is the sign, S-I-G-N, sign. The reciprocal functions, hyperbolic, cotangent, secant, and cosecant, all get negative signs in their derivatives. Other than that, they look the same as the regular trig functions. So derivative of hyperbolic cotangent is negative cosec squared, and so on. The integrals are just the reverse of the derivatives. So here are our basic integrals. Integral of sinh is cosh plus c, of course, and on down the line. So you can see that even though we're getting a bunch more formulas, they're in some ways not really all that hard to remember if we know the derivatives and integrals of the regular functions. The difference here is the signs that we come up with in our answers. So now what we're going to do is we're going to try to just use these derivative formulas and integral formulas to evaluate some derivatives and integrals. So let's start with number 1. I want you guys to try to do this. Remember that you know how to differentiate functions. Our chain rule still applies. Our product rule, our quotient rule, all those rules still apply. And this isn't written in here, but think sinh of x squared. So it's, you could put parentheses around the x squared. They really weren't necessary, but for clarity, they might be helpful. So see if you can find the derivative in part A. And while you do that, I'm going to try to figure out why I can't stay connected. I think it might have to do with me updating my iPad over the weekend. It just occurred to me there. So try number 1. I'm going to leave that screen share on. And so you guys can see that. Muted. We had y equals sinh x squared. Anybody got an answer on this one?
Yeah, I got an answer.
What'd you get?
I got cos x sine hx plus cos x sine hx.
Okay, and Aaron typed his answer in and he got something significantly different.
Oh, I mean,
So let's remember the x squared is in parentheses. And I think that Gabe, I think you looked at this as a product, but remember this is, and it's hard to type here, sinh squared. No, actually it's not, sinh x squared. Remember, this is the function we're looking at, sinh of x squared. That is not a product. Remember, that means, Cassie, that
cos of x then or something.
Okay, so I'm going to show you a couple things. On this problem, the x squared is inside the function. They didn't draw the parentheses around the x squared, but it truly intended that way. So I mentioned that earlier, but I didn't write it down. So
Yeah, I must not have heard
a
that.
little bit hard to see. Now, the other, the most common wrong answer with this problem is the one Cassie put up here. Thanks for putting that up there, Cassie. Cassie's answer would have been correct if the parenthesis would have been around the whole sinh function. So for example, if the original function had been y equals sinh of x, oops, it wants to fix that, all squared.
Are you trying to share? Like, did you write something?
It says I'm oh, I'm in that window. Sorry, I see what's going on. Hang on, I'm gonna stop share, and I'm gonna re-share with the desktop instead of just the one thing, because then when I add the chat, you guys should be able to see the chat. Can you see the chat now?
No.
Really? Well,
Unless
that's a
might-
bummer.
Yeah.
So it doesn't include the Zoom chat.
I can see the chat, but I can't see it off of your screen share. I can just still see it like in general, but I can't see it off your screen
Okay,
share.
right, yeah. So go take a peek at the chat, because that's where I put it. I'm gonna try again here. I think the problem,
Yeah, I saw it in the chat.
yeah. I am totally messed up here. Oh. So the first thing I wrote at 10:47 in the chat, where I said y equals sinh of x squared in parentheses, that's the problem we were doing here. Cassie's answer would have been correct if the last thing I wrote in the chat was the problem we were doing here. So notice the very subtle but important difference in whether it's just the x that's squared or the entire function that's squared.
Now, if it was an entire function, what would it be?
So it would be Cassie's answer that you can see in the chat just before my 10:48 post, her
Okay.
10:47 post. So she did the problem that I posted at 10:48.
That's the
Now,
thing.
in no world is this one going to be a product rule, because it really doesn't say multiply two things together. Remember, any trig function or any hyperbolic function has to have an argument, the thing inside the function. In this case, the thing inside the function is the x squared.
Weird.
I suppose you could think of it as a product if you wrote sinh x times sinh x, but then that's looking at it in that improper way as well. Okay, so let me see. I'm going to stop this share again and try one more time. Oh no, okay, okay, let's try this again. All right, so can you guys see that whiteboard? I think it's an external app problem, because every time I jumped out to Notability, where I usually write these notes, that's when it quit on me. So I think if I use the whiteboard within Zoom, I'll probably be okay. So outside function is the hyperbolic function. The inside function is the quadratic. So y prime is derivative of the outside with the same argument times the derivative of the inside piece. So 2x cosh x squared, which somebody said a while ago in the chat. So that was correct. The way Cassie looked at this is an easy sort of mistake distinction to sort of worry about. So if you had sinh of x all squared like that, then the outside function is the squaring function. And so we do 2 times sinh x to the first power times the derivative of the inside cosh x. And a quick note on this one is that we could, going back to that worksheet and all those identities, we could use the double angle identity and write that as the sinh of 2x. It's not a must, but we could. Okay, so you guys have that worksheet. Let's try letter B. So this was A, and this is a different problem. And the whiteboard should all get captured too, so we will have these. So letter B says y equals x cosh x. Which main derivative rule are you going to need here? What operation do you have in B? Product. So this one needs the
product rule.
So this is the product rule. So try this one with the product rule, see what you get, and then we'll compare. Aaron E., you are fast.
Sometimes.
I usually do this in the opposite order, but it's just my old bad habits. The first times the derivative of the second plus the second times the derivative of the first, which is just a 1. And if you're done with B and you worked ahead, I'm going to actually jump up to D. Let's do D. Y equals sech of the square root of x.
Did you say D?
D, yeah. And I wrote the problem down on the whiteboard too. So
Yeah, I was looking at the file. I was still looking at that file thing before.
okay, yeah. D, and all I wrote on the whiteboard is the problem so far.
What do you want us to do next?
Did you do D?
Yeah.
What'd you guys get?
I got -1/2 x to the -1/2 secant h of square root of x times tangent h of square root of x.
Okay. I think I agree. So I probably would have written that to start with in this order. Sech root x times
Negative root x, you mean?
tangent. Yes, I need a negative sign in there. You are correct.
Okay.
And then times the derivative of the inside, and that was your 1/2 x to the -1/2. So those are all your factors.
Pardon?
So do you have all those factors in there?
Yep.
And so you could leave it like that. I would maybe clean it up and go negative sech root x tanh root x
I'll just put it
over
2 root x.
2 root x, just to make that prettier. That -1/2 power thrown in there kind of uglies it up a little bit. All right, let's try. I want to make sure we have time to get to the integrals, so we're not going to do all of these derivatives. Let's do one of these weird sums. How about letter G? And in fact, if you want to try a few of them, let's do GHI and then report back. I don't think that will take too long. Time we can come back to some.
Are we doing the derivatives or the integrals?
All on the derivatives, G, H, and I.
Okay.
Yeah, we will jump down and do some of those integrals as well. By the way, if you want to check your work, the answers are on the last page. So as you're going, if you want to check, you can.
That's gonna be h squared, right? Not the whole sign of h x quantity squared.
Which one are you looking? It's not a, no, H is not a thing on its own. Remember, sinh is the name of a function.
I'm at x. I'm at x.
That is not the x squared. If I wanted x squared, I would say I would have had the square after the x. This says square the function. So just like with, let's see, I'm going to add a new page. Just like with our regular trig functions, when we write this, sinh squared x plus cosh squared x, we mean this. The sinh function is squared plus the cosh function is squared. The entire function is squared. And the outside function is the squaring function. If we wanted just the x to be squared, I would write it like I did in part A. And in fact, what I just wrote on the screen is what you would need to write if you were working with this function on your calculator or say in Mathematica or some other computer algebra type scenario. You would want to have the entire function squared.
Oops.
Okay. So let's see, there are the 3 problems we want to do. And so the first one involves what rule for each term? We have a function on the inside and then a function,
Oh, chain rule.
chain rule. I suppose we could use the product rule.
Oh, I
if
think you're talking about the second one.
Oh,
Oh,
okay.
no, I was talking about the first one. Yeah, I used the product because I just did sine of h of x times sine of h of x.
Okay,
Or-
but I'm going to correct you, and I'm not trying to be picky, but it's a common error, so I want to make sure that you're understanding. It's not sine of h. When we say of, sort of the next thing that we see should be what's on the inside of the function we just spoke. And this
Okay.
isn't the sine of h. So you can say sinh, or you can say hyperbolic sine.
Okay, I'm just not used to it.
We usually say sinh because it's cinchier. Because it's simpler, it's just shorter. So sinh x squared plus cosh x squared. And since it's the whole function that's getting squared, somebody said, it's the chain rule, and it is. The outside function is the squaring function, the inside function is sinh x. Now, could you do this one with the product rule? Yes. You would write sinh x times sinh x, and then you would use the product rule. However, you want to be able to do this with the chain rule, because if this is a cube or a 10th power, you're not going to want to use the product rule and have those multiple factors. Merrick, I just noticed in the chat something that didn't show up for you. Are you clear on that one yet, or do you still need that? So I think what I was trying to show you in the chat that you might not have seen was oh, you need the PDF. Got it. Okay. Let's see if I can reshare. It looks like I can't reshare, but I can I'll just drop it back in. No, not that. Okay, Merrick, is it there now for you? I just reshared the document. Oh, weird. Okay, we're gonna try this a different way. Take a little break. Yeah, and I can share it on e-learning after class too, Merrick, but I did just email it to you. So I emailed you that document and one we're going to use later as well. So you should be able to grab those from your email. No problem. Okay, so let's see if we can take a peek at G, H, and I. Now that I've got myself together. So since the squaring is the outside function in G, we're going to have y prime equals 2 sinh x to the first power times cosh x. And for the second term, the same thing, but in the reverse order. 2 cosh x sinh x. And since the order we multiply things in doesn't matter, those are like terms, and I come up with y prime equals 4 sinh x cosh x. Is that what you guys came up with? Or something close?
Yes.
Okay, I got a yes from someone and a yes from Cassie. So that looks good. All right, did you guys get to H yet? H just requires that we remember how to differentiate the natural log function. What was the basic rule there?
1 over the whatever's in the parentheses. So sine h of x. Sine h of x. Yeah, that's right.
1 over sinh x, and then
Yeah.
times the derivative. Oh, that's not, Aaron says that's not what the answer key says. So we'll come back to that, Aaron C. Thank you.
Wait,
And
what's
then
not?
times the derivative of the inside,
Yeah.
cosh x. So, but what is cosh over sinh? Go back and peek at those identities.
Tangent.
Yeah, cotangent or cof.
Tangent.
Okay, so that is not my answer on my answer key in G. Let me go back and peek at that document.
You have to have sinh and cosh rotated in your answer key.
Oh, is that the only thing that's different in my answer key for
Maybe.
G?
I'm pretty sure, yeah.
Okay, I'm gonna go take a peek. So here's the problems, all the way down to the answers. Actually, I have dy dx equals 4 sinh x cosh x. That is what I have in the answer key. Oh, okay, you look back at C, yep. And the C had the 2 x's in it, so that was a difference there. Okay. All right, what about I? I think I is pretty straightforward, right? Because E stands for easy. Derivative of e to a power is e to the power times the derivative of the power.
Yep.
And that's actually fine, just like that, or you can reverse the order. All right, let's try, we'll do that later. Let's try some of the integral problems. Remember, we're going to integrate, essentially we're doing the same thing only backward. So let's try letter A, which is a definite integral. Little line here. And we'll go to letter A. Let me see if I can. Do this without messing up.
Is this for part 3?
We've got integral.
Is this for part 3?
The number 3, letter A.
All right.
Integral of sinh x dx. And then we're evaluating from 0 to 4. And just like with other problems, we can check these on the calculator. We can check in Mathematica so we can make sure we're getting them correct. Okay, so back to our little handy dandy formula sheet. And we haven't been using these for long, but remember the derivative and integral of sinh is cosh. Oh, that's nice. We don't even have to worry about the sign. So this is cosh x evaluated from 0 to 4. Now I am good with you guys doing this totally on the calculator from here on out, but I do want to show you why the answer ends up the way it does. So we're going to go ahead and evaluate by hand one time and then sort of think about why it works this way. So let's see, evaluate at the upper limit, cosh 4 minus cosh 0. So we could go take a calculator, get a decimal answer, maybe get an exact answer in terms of e to a power. But here's what this is doing when we're calculating it. It's e to the 4th plus e to the minus 4th over 2. And then minus e to the 0 plus e to the minus 0 over 2. So that's evaluating. Sure, I'm still sharing. Yeah, I am. That's evaluating at 4 in the first fraction and at 0 in the second fraction. So in an exact form, in terms of e, this would be e to the 4th plus e to the minus 4 over 2 minus, let's see, e to the 0 is 1. So this is 1 plus 1 over 2 minus 1. So that's the answer in exact form. And then you can easily evaluate that. But you can also just enter that function on your calculator, cosh 4 minus cosh 0. And so I think this is actually a good time to show you some things in Mathematica. So I am going to share
Before you
screen.
switch over, the 1 plus 1 for the second step there you have.
Mm-hmm.
I'm just saying e to the 0 is 1 and then plus e to the negative 0 is 1.
E to the, yeah, because negative 0 is just 0. Negative 0 is no different than 0, right? The negative of something means it's opposite, and the opposite of 0 is 0. So e to the negative 0 is, yes, absolutely, also positive 1. Notice that this is probably worth remembering. For this whole thing, we got the number 1. Cosh of 0, just like cosine 0, is 1. So another way to write this in exact form would be cosh 4 minus 1. Notice that cosh 4 is a pretty big number because it's e to the 4th plus something tiny over 2. You know, it's not, maybe not huge, but e to the 4th, 3 to the 4th is 81. So this is on the order of, you know, this is probably 70-ish or something. And then divided by 2.
Is there a specific way to enter that in on like the inspires? Because it just keeps giving me cosh 4 minus cosh 0.
Okay, so if it's giving you the cosh 4 as your answer, it's because it's giving it in exact form. So if you do second and then entry where the little squiggly equal sign is, you can
Yeah,
get an approximate amount.
I did that and it's still
Okay, so
just,
how did you enter cosh?
I just put cosh 4 minus cosh 0 and it keeps, when I hit enter or even the control squiggly lines, it's still doing the same thing.
Okay, are you on the Inspire CAS or are you on the?
Yes.
Okay, so are you putting the 4 and the 0 inside parentheses?
No.
Try that.
Okay. And am I just supposed to be typing it out, the cosh
You
part?
can, but you can also find that in the catalog. So you can go to the catalog and you can find that function, but typing it out is fine. You can
Okay.
type out any function on the Inspire CAS and it will work. Let's see. Let me see if I've got my
Yeah,
here.
it gave me an actual number. Well, it's just the actual number of cosh 4 minus cat. Oh, I accidentally hit cash. That's why.
so then it thinks that you want cash to be a variable, and it just gave you cash
Yeah.
back probably. That's
So yeah,
funny.
I think putting it in parentheses will end up working.
Yeah, the Nspires and the TI-89s were the same way. They're very picky about syntax. They're a little bit more lenient on the TI-84s and the Nspires that aren't the computer algebra system, so you can kind of get away with a little bit.
Mhm.
But yeah, they're gonna want that sort of like this. So
So
this fixed it when you went.
well, it ended up giving me the cosh 4 minus 1. And then if I
Okay,
did the
right.
squigglies, it gave me an actual number.
Yes, and that's what it's going to do. So it's leaving it in, and the number that it's calculating, it's doing this. It's e to the 4th plus e to the minus 4 over 2, and then it's subtracting the 1.
Okay, which answer do you want, or like will we have to put in on the program?
If it doesn't tell you, it shouldn't care.
Okay.
So if they want you to leave it in terms of the hyperbolic functions, they should tell you to do so. If they want an estimation, they should tell you to do so. We can look at a couple in a minute. I want to jump over before we do too many more and look at Mathematica so you guys can see how that works. I know some of you have gotten it downloaded. There were some issues over the weekend with the server and they had to reset it, but it should be working now. So if you had trouble getting it to work and you were getting an error message when you tried to go in there, go ahead and try again. Because Merrick and I had the same problem, and someone got back to us on the weekend and said they fixed it, and it was fixed for me. Merrick, is it fixed for you?
Were you talking about Wolfram?
Yes.
Oh, yeah, it did that for me too, and it's working now.
Okay, good. All right, and Merrick says it's working for him now too. So I'm gonna go ahead and add another page. Let's do one more integral where we have to do a substitution, and then let's jump over to Mathematica so we can see how it would treat these. So which one of these looks maybe kind of messy? How about G? So G is an improper integral this time. Integral of sec squared root x over root x dx. And this one we don't have to evaluate. We just need to come up with a function. And we should be thinking, let's see, sec squared. So our answer should look something like a tanh, right? But there's going to be a sign difference in there. And then we have this messy square root hanging about. So let's go ahead and make a substitution. What substitution might I make on here? Let u equal square root of x. And then du equals, and you know, I know a lot of you go ahead and do the x to the 1/2. I honestly think this is worth remembering. 1 over 2 root x dx. Do you absolutely have to memorize it? No, because you can develop it every time, but every time you're going to get that. So I think it's worthwhile to sort of put it in our memory banks just so we don't have to go back and develop it each time. All right, that means that dx is equal to 2 root x times du. So I'm going to put in that substitution. Sec squared u over root x do 2 root x times du. And notice that the root x's cancel. If you turn those into u's, that's fine. They still cancel. And we can factor that 2 out. So we have 2 times the integral sec squared u du, which is -2 No, it's not. Undo, 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 which is 2 tanh u plus c. So remember the original 3 functions, sinh, cosh, tanh, all have derivatives and antiderivatives that are positive. It was a little bit harder to remember, but if we float back there, integral of sech squared is tanh, so we're good. Okay, so I am going to share screen. I'm going to go ahead and continue, so I'm going to kill the other screen share, and we're going to go to Mathematica and take a peek. So there's my Mathematica screen, and are you guys seeing the whole thing? Can you guys see a problem where I had the f of x equals sinh x squared plus
Yes.
cosh x? Okay. Top of that is not showing on here. But let's look at those last 2 that we did. So the first one we did was to integrate. And what were we integrating? Sinh x. So keep in mind that when you enter a function in Mathematica, they're very picky about some things. And the one thing that they're very picky about is that function names always start with capital letters. So if I write lowercase SINH, it's not going to work. Remember, you can also get around this by using the palette, because then you can go find the function. Sinh x. And we were integrating that from 0 to 4. So x comma 0 comma 4. I think that was right. And if I hit Shift Enter, -1 plus cosh 4. And that's right? We had cosh 4 minus 1. Notice Mathematica will also give you the numerical value, and that usually shows up in the things you might want to do next. So we can go numerical value, and it's about 26. So if we needed the estimation, we can get it really easily. Back up here, I don't know if there's a way that we can write this in terms of a power of e or not. It's not in the options. So I think that in Alta, this will always be okay. It should be. Unless they want the approximation, then you'll go to the approximation. Let's look at that next one. That next one was to integrate, what was it? SECH of the square root of x. So this one's going to require a little bit of extra nesting. And oops, that function was squared. So I'm going to need parentheses around that. And then that was divided by square root of x. With respect to x. And so just like on the Inspire calculators and on the TI-89, you do have to specify that you're integrating with respect to x. So that little comma x is essential in there. And what it must not match. Oh. I need another set of parentheses there. Okay, 2 tanh square root of x. Is that what we had? I might not have gone back and put the square root back in my final answer. I think that's what we had. Notice that Mathematica does not give us the plus C, so we have to remember to put it in there. Oh, here's an interesting thing though. Notice that this will, if we don't have an estimation or a number, it will let us convert back to exponential form. So there that is in exponential form, 2 tanh x. That is ugly, but it's doable. Here's an interesting next thing we can do, x derivative. So sometimes these are kind of fun. Well, that got really ugly. Full simplify. So full simplify will take that ugly mess and simplify it as much as it can. Notice it gave us back sech of square root of x squared. So the function, the sech function squared over square root of x, which is exactly what we started with. And that makes sense because if we integrate something and then we differentiate it, we should get back to where we started. Notice their notation is slightly different, but there it is. So we're in pretty good shape there. And again, we could write that in terms of exponentials if we wanted to, but let's not go there. What am I doing here? Let's try one more where we have limits. Why don't you guys try letter E? The integral from 0 to 1 square root 1 plus sinh squared x. So we'll take a few minutes, give letter E a try. I'm going to switch my screen share from Mathematica to that document again. So 3, letter E. Give me a yes in chat when you think you have 3E done. We'll compare. Remember, you're evaluating on this one, so you should come up with a numerical answer. Okay, Merrick and Aaron C are done. one's done. Did you guys check your answer with what was in the back to see if it matches? I got a yep from Aaron C. Okay, so integral from 0 to 1 of square root 1 plus sinh squared x. And this is one where you can try to fiddle around with it in other ways, but where you might want to look at the identities. So looking at the identities for the hyperbolic functions, 1 plus sinh squared x is 1 plus sinh squared x is cosh squared x. So we have integral of the square root of something squared. So sometimes when things look messy, it's a good idea to look back at identities and see if you can simplify things a bit. If I take the square root of a perfect square, I get the absolute value of whatever is on the inside. Because remember, we need to make sure that whatever we take out of there is positive. But then also remember that our cosh function is that hanging cable that's all above the x-axis, so it's always positive, and we can actually leave off those absolute values. If this was a different function, we might not be able to do that. And then integral of cosh is sinh, so we have sinh x from 0 to 1, which is sinh 1 minus sinh 0, or just sinh 1, because that thing is equal to 0. E to the 0 minus e to the minus 0 is 1 minus 1 over 2. So sinh 1 in exact form. And again, if you want to estimate, you can. Mathematica tells me that sinh 1 is about 1.17. $1.175. So
Those absolute value bars.
those are absolute value bars, because remember that when you take the square root of something squared, in general, square root of, we'll use a z to not confuse it with the x in our problem. Square root of something squared is the absolute value of z, because the square root means the positive square root. And so if z happened to be negative, you would need absolute values. Now in this problem, we were able to just completely eliminate them right away, because our cosh function is always greater than or equal to 0. So we were okay with getting rid of them. If it wasn't greater than or equal to 0 on this interval from 0 to 1, then we would have to take that into account when we evaluate that integral.
But you're saying it's greater than or equal to the 0 because it's
What does it look like? It looks like this, right?
but you're saying that because it's from 0 to 1, right?
But in fact, in this case, it's true for all x values, right? Because here's
Oh.
there's what the hyperbolic cosine looks like, roughly.
Therefore, you can't have it.
A
You
really
can't
ugly graph, but that's roughly my hanging cable, right? Is the hyperbolic cosine ever negative? No. The y value never actually falls below 1.
so the limits couldn't be negative then.
No, the limits could be negative. Remember, these are x values. I think you're confusing x values and y values. This function is defined for all x values. So the limits could be whatever we want.
Okay.
And no matter what the limits are in this problem, the hyperbolic cosine is greater than 0. So I am able to eliminate the absolute value because hyperbolic cosine is always greater than 0. If this was a regular cosine function, then I'm going to have to be more careful because the regular cosine function does fall below the x-axis, although not on the interval from 0 to 1.
It's always greater than or equal to 0.
Or equal to, right? Absolute value of 0 is 0. This function, however, is always greater than 0. Its minimum value is 1, which is greater than 0. So the hyperbolic cosine function is indeed, it is always greater than or equal to 0, but it's also always greater than 0.
And that has nothing to do with the limits, right?
In this scenario, it doesn't matter what the limits are because whether we were from 0 to 1 or -3 to -1, the hyperbolic cosine function is greater than 0. In general, it will definitely have to do with the limits. And you will have to look at that interval and see whether or not your function is positive on that interval.
Okay.
And if it's not, you will adjust accordingly.
So the y values can never be less than 0, right?
Well, I mean, if they are, then you have to realize that this is going to take on something different. So for example, here, let's do this. If I had the square root of, let's take something, let's just do cosine squared x. That would give me the absolute value of cosine x. And let's say that my limits of integration were from what do we want to do? Let's go 0 to pi. Well, from 0 to pi over 2, the cosine function is positive. But from pi over 2 to pi, the cosine function is negative. So what we would do is we would split it up. I don't want to get rid of my page. We would split it up at x equals pi over 2 and use 2 separate integrals. So let's worry about it when we come to it, and let's not dwell on it right now. But you would have to account for the fact that that function is negative on a portion of your limits of integration. Okay?
Yeah.
I don't want to get muddied in this right now.
Thank you.
Okay, and no doubt it will come back to us later. But right now we don't really need to worry about it while we're trying to figure other things out. So I'd rather you try to figure the other stuff out and we can worry about this piece later.
For that square root cosine squared x, that's for the.
That was just, you asked me for a different kind of example, so I made up a different example that has nothing to do with the problem we just did.
Right. I was just making sure the split and that were together. The split
So
thing.
if we were integrating that function, yes, we would have to split this up. Okay, I am going to send you guys one more document. Okay, I already sent this to Merrick in an email since he had trouble getting it. So there is a gateway arch document. And there's the document. Okay, so there's a nice picture of the gateway arch, and here's what looks like an ugly representation for the equation of the gateway arch. But notice something about this. Even though this is ugly, it's mostly ugly in terms of numbers and not in terms of functions. So looking at the inside of this, notice we have y equals, and then we've got this coefficient. The negative coefficient is what makes this thing open upside down. So that kind of makes sense. And then we have the hyperbolic cosine of this weird thing. And why they didn't simplify this in this form, I'm not really sure. And then that -1, there's a -1 in here. So this -1 is outside the hyperbolic cosine though. And then we're adding 630 to all of that. So just take a look at that for a minute. Okay, so we've got this gateway arch problem. And I'm going to switch my share and jump over to Mathematica, where I did the plot. So here's where I entered it. I called it arch of x. So there's my arch function. And there's the plot of that thing. And I plotted it from -315 to 315 because that's actually where we see the arch. Notice it looks like it's a little over 600 feet high. In fact, it's the 630, so it's 630 feet high. And this problem is asking us to find the maximum value for the arch. In other words, how high is it at its highest point? So we can kind of see from our picture over here that its highest point is right here in the center at 0, and its highest point is that 630 feet. Now, if we weren't doing this graphically and just sort of looking at the graph to come up with this, what would we do? Well, how did you guys find maximum values for functions? How did you do that? Using calculus. Think back to Calc 1. How did you find the maximum value or the minimum value of a curve? It was the place where the something it was equal to something. Let's do this, plain text. I can put this here. How do you find the maximum?
What'd you type in to get that? So output that.
Right above, arch X. It's on my screen. That's the way I typed it in. There's how Mathematica output it. And then I did plot that same function. And I just clicked plot and it gave me this. It had different limits for the X value, so I had to change that to -315 to 315. But my question is, how do you find the maximum value on a curve using calculus?
Someone answered in the chat. I think Merrick.
Oh, Merrick did? Okay, I got my chat hidden. Slope of the tangent line equals 0. And so how do you get the slope of the tangent line? I'm going to play devil's advocate here and dig a little derivative. So yeah, we're going to find the derivative. We're going to set it equal to 0. And then we're going to solve. Okay, so that's how we find the maximum value. How about number 2? How do you find the length of the arch? Using calculus again. So when I say the length of the arch, I mean starting here, how far would an ant have to travel if he crawled all along the arch to the opposite end, or a person? So we go from here to here. How do we find that arc length? Do we have an arc length formula?
Yeah.
Yeah, so that would you would use the arc length. Okay, let's see what number 3 said. The area under the arch. Wouldn't we integrate the arch function? The function I called arch of X. From where to where?
0 to our maximum.
Nope.
300 to 300, I mean.
Yeah, -315 to +315.
Oh, that's
okay. So it is 11:54, so we need to sign off in about 1 minute. So I have just a little bit of time in between my classes because I have another class right at noon, and you guys might too. So we're gonna leave it here. I'm gonna share this. I'm gonna share this document with you. So if you've got Mathematica already downloaded, you're good. If you don't have it downloaded and you have like an Inspire CAS where you can evaluate derivatives and integrals nicely on the calculator instead of doing the crunchy, ugly stuff by hand, because this formula is really ugly with these numbers, you can do that. But what I would like you to do is I would like you to try to answer those 3 questions using technology, either Mathematica or some form of CAS like Inspire, or you could even go off and set them up in Wolfram Alpha if you wanted to. Okay, so I will save this and I will put it up. I might not get it up until after my class because my next class goes from 12 till 2. But I will get it up there this afternoon so that you guys can have this to start with. That way you don't have to re-input all the stuff from earlier.
Thank you.
Okay.
No,
Bye-bye. Have a good day, everyone.
You too. Thank you.